Okay, well, I think I should at least start the introductions and get people back to their screens by talking loudly. So we are back for the third session of FPTalks 2023. And in this session, we'll see a lot on verification, correct rounding, and error bounds, which has always been a popular topic here at FPTalks. To kick the session off, I've got Tue Ly is here. He's a software engineer at Google and more importantly on the LLVM project. And he's going to be talking about maintaining the LLVM libm implementations. So Tue, please take it away.
Thank you, Pavel. And hello, everyone. So today, I'm going to give an introduction to the project that we have for about 2 years that we're implementing the libm inside LLVM libc. So first, so what is LLVM libc? This project started about I guess 3 years ago. It's to implement the libc inside the LLVM umbrella. And now we aim to be a drop-in replacement for the legacy libc on any platform. And and so we in our build system we have the overlay build mode, so that will allow you to slowly roll out function by function selectively. And the license of the library allow you to do the static linking and build from source for it. So everything is implemented in C++, just like most of the LLVM umbrella. And so we would like the code to make it look and feel like modern C++ library. So here's the homepage to the project and the GitHub link. So how about the math function in the LLVM libc project? So our goal is to implementing all the C99, and thanks to Paul, now we are aiming for the C23 math functions. And we may include other functions that outside the C standards, such as the reciprocal square root or the sine cosine. And we would aim to support for all the floating point format-ish in the C standard, single, double precisions, extended double, and quad precisions. And we support most of the platform that we're interested in, like Linux on x86, AR64, and the new platform RISC-V. On Windows, x86 64, and also the AR64 if the Windows on ARM fully materialized. And on Mac OS, we currently support on both Intel and AMD. Sorry, not AMD, Intel and M1. And currently there are efforts from AMD side to port the libc to the GPU, and they do have working examples for NVIDIA and AMD GPU. So Intel might need to have set up something on there. And there are also parallel effort to make this libc work on the bare metal use case, especially for ARM32 and RISC-V 32. So for the status page of the math functions, here's the link. So our math functions library has two highest priority, and the first one is the accuracy. So when I started about 2 years ago, we have a discussions of what is the trade-off, how should we implement those functions between the performance and accuracy. And in the end, we come up that in the first implementation, we should aim for as accurate as possible, because it's going to be much easier once people roll out to make things faster later than we make things more accurate but slower later. And people are going to be much harder to accept that. And so I reached out. At that time, I found out there are two current ongoing projects about implementing correctly routed math functions. They're the Core Math project and the libm project. And after reaching out to them, their work inspired me to make the requirement or make the goal to implement the libm to be correctly routed to all routing modes. Currently, we set and test for the 4 standard routing mode. But I know that, for example, on ARM, they have an extra one that we need to add and test if needed. And we do test the accuracy on most of the platform that we could, but some platform we might have to loosen the, for example, like the embedded system where they don't have enough memories to store the big tables, or for GPUs due to some code size or memories or performance, or even the FPU accuracy where they just completely drop off the normal part. And for the performance, we would like the libm to be usable in production, so it should be comparable to other accurate libm library, or mostly the GNU libc library. But we also need to avoid the pitfall of the IBM accurate math library, in which they have extremely high latency in the worst case. And for the performance purpose, we can totally utilize the platform-specific instructions whenever applicable, especially for newer platform turning up, like GPUs or the RISC-V. So why is accuracy important? So the correct routings will actually imply one of very important properties is consistency. If the math function output is consistent, is correct routing, it's going to be consistent across the platform and the library versions. And that will actually significantly reduce the toll when we update or integrating the libraries, or whenever a new glibc. So at Google, whenever the new glibc rollout is actually a big effort that takes months, because especially on the math side, because a lot of the golden files need to be updated, and it's spread across multiple teams. And to update them is it's just a lot of work, and it takes too long. So with the new functions, that correctly routed function that we roll out in Google Productions, is we pay the first time cost for updating those tests when we roll out. But after that, all the iterations is actually extremely quick and effortless. So no more. Also, like, because the output is going to be identical across the platform, so no more if-def for switches in the golden test, and no more updates when we roll them out. And actually, any of the new performance improvement, as long as we can guarantee the accuracy, we can just immediately roll out without anyone notice, maybe from the except from the performance side. And moreover, now the golden test is not going to be a burden anymore. It might be the things to keep track of, so that you can make sure that the system or the algorithm is correct. It make it similar to integers golden test. So for our library, we implement in mostly in C++. Right now, they are I think they use C++ 17, and it's slightly different from other math library, because they are mostly implemented in C and a lot of assembly. So there are some nice things in C++. Is using the templates, and we can simplify a lot of macros. I think one of the hardest one when I was learning how glibc implementing math function is a lot of macros.
Tue, I think we're getting some bandwidth artifacts. I'm going to turn your video off to see if that helps.
Thanks. Let me. Is it better?
Yeah, I turned your video off, and hopefully it's going to be a little better.
Okay, thank you. And also, like, one of the hardest problem in programming is naming. And so with C++, we are allowed to overload the function names and operators. So the number of names I have to come up with is a lot less. And also with namespaces to help to organize the code. So what did we utilize to implement the math functions? Is that there are a lot of recent advances in floating point arithmetics, especially in the worst case analysis, as a lot of people mentioned. So previously in the IBM accurate math library, I think the worst case, they bump it up to 800 bits. But now we know that a lot of math function can be in double precision can be done with a lot less than 200 bits. And there are many tools to generate the polynomial approximations, like the Solias or the libm project. And there are many tools to analyze floating point errors from Kappa to SageMath. So also we intensively implement with the modern CPUs. They have fused multiply add and floating point routings or others extensions. There are many difficulties, of course, in implementing. So our libc is built from ground up, and there are a lot of building modes where we assume that no other libc, and so there are problems with circular dependency with the built-in compiler built-in, because some of the building modes, those floating point built-in actually make call back to the C library, and also managing the platform dependence on those, and also the problem with optimizations on the new platform that doesn't have the compiler built in yet, such as the RISC-V or the ARC64 if we don't rely on the built-in FMA. Also, the detecting routing modes for exceptional cases can be expensive. So how do we test, make sure that our library is correct? So we, at the first round, we have unit tests for exceptional case and some hard to route inputs. And those are running on pre and post commits on the LLVM project on all the supported platform. There are some platforms we are trying to turn up the bots. And we have the exhaustive test for all the single input, single precision math functions that is running. And right now it's running bihourly. And we have the first test for the rest to randomly generate and check against MPFR. Also, the core math projects, especially Paul and the LLVM project, help us to independently verify the accuracy of our implementation. So next, I'm going to talk about how the performance of those functions that we implemented so far. So for the setup, we use Ryzen 5900 on Ubuntu and using Clang 15. And for the micro benchmark test suite, we use the performance test from the core math project, and we compare against the system library, which is the glibc version 235. So here's the throughput when we up the around almost 30 functions that we implemented. There are some double precisions function in there for the log functions, and the rest are single precisions. And we can see that the performance of most of the function is within the bound that I artificially set, is within 2x of the glibc implementation. So the blue line at 1 is the glibc, and the green part is the throughput compared with over glibc of using the FMA on x86-64. And there are a lot of functions that we are faster than glibc, and we are able to identify like 6 functions where glibc will need improvement because those are, we are about like 4 to 6 times higher throughput than glibc. And here's not only the throughput is good and better than glibc on average, the latency we are able to cutting down also, and especially on those 6 functions that I mentioned on the throughput, the latency is also very bad on glibc implementations. So those are, I think, the immediate part that can be taken. There are some spike on the red in here, which is where we don't use the routing and we don't use the FMA instructions. But I think those that can be fixed or improved. But right now, most of the CPUs on the x86-64 work, we have at least FMA AVX2, so that is not urgent. So in summary, compared to the glibc on x86-64 on our system, on average, the latency we reduced by 23%, with the maximum about 70% using FMA or SSE 4.2. The throughput, we more than doubled the throughput on average, and the best case, it can reach into like 5 to 6 times. We also help Paul to port the test bench to the performance test bench to ARM64, and we run them on various ARC64 devices like from low power like Raspberry Pi or Raspberry 3 to the Cavium machine, which is the high performance ARM CPU, and we got similar improvement, but the number is not as big in here because so there are room for improvement. And so the latency improved is only like 1 to 2% on average. The maximum is still 50%. the throughput, we have about half the numbers. But definitely, if we can set it up and do some improvement for the AR64. So in summary, there are 6 glibc functions that we identified that urgently need more efficient implementations. Among them, especially the hyperbolic tangent on float, because this is actually the hottest functions, the hottest math functions that is not matrix related due to the machine learning and AI. So what's next for us? Our goal is actually for the libm is actually pretty simple to complete all the C99 and C23 functions and add more support on other platform and use cases. And there are already some requests to consider have a specialized implementation for fast math, and we'll see how if we have power or time to do that, and also fine-tune the performance further. So
Okay.
I'd like to give special thanks to all the LLVM libc contributors and reviewers, and especially to the COMAT project and LLVM project to help us kickstart and help the project going, and all our researcher implementers in the field. Thanks. There's a link to. Yeah. Thank you.
Yeah, I'll make sure to post links to anything to the project on the website. And we're a little over time, so I'm just going to move straight on to the next talk. But Tue, there's a bunch of questions, like quite a lot in the Slack. So if you have a chance to get to those, I'm sure that we can continue.